Um, right. So and so therefore beta is equal to, we know beta is equal to 1 by kt. Right? We need to get out of this dou u by dou beta, because that, to make it more mathematically simplified. So dou u by dou beta, we need to replace it by, instead of in terms of t. So beta is equal to 1 by kt, or therefore you can write dou beta is equal to minus 1 by kt squared dou t. Therefore dou by dou beta is equal to minus kt squared dou by dou t. So therefore I substitute this identity with this one over here, right? So then I can write, instead of dou u by dou beta, I can write kt squared, right? I apply this expression over here. Kt squared dou u by dou t is equal to variation delta E, and therefore delta E is equal to kt squared. What is dou u by dou t? It is Cv, right? Heat capacity at constant volume. So kt squared Cv root. So therefore this is actually telling me the root mean square. So it's a mean and it's a root. Then so root mean square fluctuation. So delta E is equal to the root mean square fluctuation in energy is equal to root of kt squared Cv. Okay. And then for the same system, I can define something called the relative fluctuation as delta E by E. Delta E by E. Instead of E, I will straight away use the expression for U, which I can write it as kt squared Cv divided by U. Then let's try to substitute the expressions for the Cv and the U for an ideal gas. So we know that for an ideal gas, we have derived, you must have derived yourself, or you must be knowing from BSc, that U is equal to 3 by 2 nkt. You can, based on our derivations, you must have done it. U is equal to 3 by 2 nkt, and therefore Cv is equal to 3 by 2 nk, right? So let's substitute that over there. Then you will get the value delta E by E is equal to root of kt squared 3 by 2 nkt divided by 3 by 2 nk, which on substitution I will get it as 2 by 3 root of 2 by 3n. Generally, U is directly proportional to n, or Cv is directly proportional to n. So therefore here delta E by E is directly proportional to 1 by root n. So this is in general for a ideal gas, right? So in general we can write it as delta E by E is directly proportional to 1 by root n. So what does this expression tell me? This expression tells me that as n tends to infinity, what happens? As n tends to infinity, my delta E by E will tend to 0. Okay. So as n tends to infinity, delta E by E will tend to 0. Delta E by E tends to 0 projects a situation that there is no fluctuation in the energy. Right. So what can I conclude there? So thus for systems with large number of n, the number of particles, the relative RMS fluctuation in the value of energy is negligible. So which is very relevant in the case of statistical mechanical situations, because in the StatMech we deal with systems with very high values of n, right? That is why we are able to apply the statistical expressions over there. So that is it. So we started with the general system of the ideal gas, and we found that as n tends to infinity, the so-called the energy fluctuation tends to 0. So therefore that might be the situation. So energy fluctuation tend to 0 means that is what I conceived for the basically for the microcanonical ensemble. Although in the case of canonical, I do start with a delta E assumption. I do allow the energy to fluctuate between the elements. But since the number of particles are very huge, tends to infinity, in those kinds of situations, the canonical ensemble and the microcanonical ensemble formulations tends to be same. So that might be the reason for the kind of the paradox with which we started this correspondence between the canonical and the microcanonical ensembles. Okay, that's it.